This conference will now be recorded.
Hello everyone, last day we have seen how to calculate pH of a solution. Okay, now some more information related to pH scale we have to know. The other topics that we are going to discuss today is relation between pH and pOH. So just like pH, there will be another term which is pOH, and that is related to hydroxide ion, then ionization of weak acids and weak bases and related problems. So what is pH scale? This is basically a logarithmic scale where concentration of H plus is expressed as by taking negative logarithm of H plus, and that is actually pH. So as we can calculate pH, similarly we can also calculate pOH of a neutral solution. So if negative logarithm of H plus concentration, if we are calling it as pH, so just in place of H plus, if you put HO minus, then it will be known as pOH. Okay, and we have already seen that pH of neutral solution, it may be pure water also because that is also neutral, it is actually equal to 7. So just like pH, pOH, that is also equal to 7 because H plus concentration and HO minus concentration both are same in neutral solution or pure water. So that is why when you are saying pH for neutral solution, it is 7. So using the same expression like minus log H plus concentration, you can also use minus log HO minus concentration, which is pOH, and that is also equal to 7, but for neutral solution or pure water. But when it is acidic solution, obviously now you have to remember that concentration of H plus or H3O plus, it is greater than concentration of HO minus. And in this case, H plus concentration, that will be greater than 10 to the power minus 7. And in terms of pH, you can say that it will be greater than 7 because when H plus concentration is greater than 10 to the minus 7, so obviously, sorry, it will be less, not greater, because there is a negative sign, so keep that in mind. So pH will be lesser than 7. Similarly, when it is a basic solution, now the concentration of H3O plus, that will be lesser than 10 to the power minus 7 because now HO minus concentration is greater than 7. So when it is basic solution, basically now pH will be greater than 7. And if you are writing in terms of pOH, it will be completely reverse. But general convention that we follow, it is mostly we express it in terms of pH, that is concentration of H plus, that we express in terms of pH. So when it is equal to 7, it is basically neutral. When it is greater than 7, it is basically basic solution because in that case HO minus concentration is greater than 10 to the power minus 7 and H plus or H3O plus concentration is less than 10 to the power minus 7. And if it is acidic, then pH will be lesser than 7. So this is the summary that we can draw from all this discussion. Basically, the discussion that we have started in the last class, you have to start from there, not the discussion that we are doing in this slide only. So it is basically, it already started from the last class and we are just continuing the discussion for pH scale. So the summary of this total discussion, it will be as it is mentioned here. So remember, in terms of pH, these three things you have to remember. But if you are saying that in terms of pOH, now it will be reversed. But general convention is we follow pH only, not pOH. But if you are getting any problem that is asking for pOH, so read the question carefully when you are solving problem because sometimes it may ask the pOH of the solution also. So in that case, don't confuse pH and pOH because these two are different. Okay, here we have in our day-to-day life we see some different things for which pH, some of them are food also, food related items, but not all of them. So here some food items or day-to-day basis we use some household products, or we also have some biological things. See, here we have starting from 0. This is basically the pH scale starting from 0. This is the middle point, which is 7, and when you are moving beyond 7, it is basically now basic zone. or alkaline zone. So this zone is alkaline, this zone is acidic, and this zone is neutral. So 7 or around 7, that is in between 6 to 7 or 7 to 8, that is actually neutral. Here we have in the extreme acidic side, that is battery. So the acid that is used in battery, it is basically concentrated H2SO4, so which is having minimum pH, that means it is very strong acidic solution. Then stomach acid, we know it is HCl, pH is 1. Then in lemon it is around 2, then vinegar, and gradually the acidity is decreasing as we are moving from vinegar to tomato to coffee and milk. Milk is almost neutral. Then in case of blood, it is gradually moving towards alkaline. Then stomach tablet means sometimes to neutralize the excess acid secretion, that is abnormal excess acid secretion in the stomach acid, we have to take some pills. So that is to neutralize this excess acid. The neutralization is possible only if you are using some alkaline solution. So that is why stomach tablets, it is around 10. Then soap, and ultimately drain cleaner, which is maximum basic. Here we also have baking soda, which is used in cooking, not in cooking, in other household work also. Ammonia solution, bleach, and maximum alkaline, it is drain cleaner. To remove the blockage of drain, we use this type of highly alkaline matter. Okay, so this is the pH scale, and you can see examples of some known items. Now we have a problem. Which of the following salt will give maximum, that is highest pH in water? Now highest pH means what? You have to find in which case basic solution will be produced, right? Now here we have total four salts given in options ABCD. So KCl, the salt, if you want to know when you have taken these salts in water medium, what will be the nature of the solution, basic or acidic? If we want to know that, basically we have to understand from which acid and base this salt is actually produced. So KCl is basically produced from KOH and HCl. So this is a neutralization reaction, but if you are considering the hydrolysis reaction, that is you have taken salt in water, then here KOH and HCl will be produced. Now both are actually strong. This is strong base, this is strong acid. Now when is this strong base and strong acid? We know that strong acid to strong base, they dissociate completely. So in this case, number of HO minus ions, that is a concentration, that will be equal to H plus that is generated from HCl, because from 1 mole of KCl, it is only 1 mole of KOH you will get, 1 mole of HCl you will get. So it is always 1:1. So the number of HO minus is always equal to H plus, so it will always be a neutral solution. So in short, in brief, I can say that if it is any salt which is made from strong acid and strong base, it is always neutral, it is always producing neutral solution, right? Now come to the second one, NaCl. Now that is also same thing, because now instead of KOH, it will be NaOH and NaCl, but same explanation. Then Na2CO3. Now Na2CO3, here also NaOH, though it is 2 moles of NaOH, but it is strong base. But what about the acid? Acid is H2CO3, carbonic acid. Now this is weak acid. So strong base and weak acid, in this case what will happen? NaOH will be completely dissociated. So now you cannot say that the number of HO minus that are produced from NaOH, that is not equal to the number of H plus that is produced from H2CO3. Number of moles, there is no such problem, because 2 NaOH means 2 HO minus maximum can be generated, and H2CO3 means maximum 2 H plus can be generated. So number wise it is always same, but percentage of dissociation from strong base and weak acid, it will not be same. So number of HO minus, it is not equal to number of H plus. Basically it is greater than, not equal to, and it is greater than. So it is basically a basic solution. So if it is basic solution, that means it will give highest pH. What about the last one? If you are considering it CuSO4, that means it will be produced, the corresponding base is CuH whole 2, which is basically weak base, and the acid is H2SO4. This is strong acid. So in this case, pH will be lesser than 7. So it will be towards acidic side. It is not giving you highest pH, that is among these four. So option D, it will be lesser than pH. Option C is greater than 7. Option D lesser than 7. Option C greater than 7. And KCl-NaCl, it is neutral. So that is why correct option will be the third one. So here the logic is Na2CO3, which is a salt of NaOH, and H2CO3 weak acid, it will produce basic solution. pH will be greater than 7. So correct answer is sodium carbonate, option C. Next problem, at 100 degrees centigrade, Kw, okay, that is, remember auto ionization of water that we have already seen. When you take water, there is auto ionization to A, though it is very ionization is very less. So this type of ionization, if you are putting here a 2H2O, then it will be in terms of H2O plus and HO minus. So this is ionization of water, for which if you write the equilibrium constant, that is actually Kw. So it is the ionic product, and in the denominator we are not writing H2 because it is present in large excess, so its concentration will not change. At 100 degrees centigrade, Kw of water is 55 times its value at 25 degrees centigrade. So when you are increasing temperature from 25 degrees centigrade to 100 degrees centigrade, obviously the value of equilibrium constant will increase because it is dependent on temperature, and increase is 55 times, very high. So it is asking, from this information you have to find what will be the pH of a neutral solution at 100 degree centigrade. Fine. So 25 degrees centigrade, we know the value is 10 to the power minus 14. 1 into 10 to the power minus 14. But when it is 100 degrees centigrade, the value is 55 times high. So this information is basically giving you the Kw value at 100 degrees centigrade. So if you know that, from that you have to find first H plus concentration, and once you know the H plus concentration, the second step is, next you have to find minus log H plus concentration, and that is actually the pH. So in this way you can find the pH, and it is obviously neutral solution because it is water. Here log 55, that value is given 1.74. So it means we have to use this value. So at 25 degrees centigrade, Kw is equal to H plus concentration and HO minus concentration, that is the ionic product. You can also write H2O plus, it doesn't matter anything. So this value is 10 to the power minus 14. And when you have increased the temperature, now the value is 55 times high. So this information is already given in the problem. So if it is so, from this, as these two are present in equal concentration, so H plus concentration, how you can get? By taking root for this 55 into 10 to the power minus 14. So in the right hand side, if you take root, you will get concentration of H plus. As it is neutral solution, so these two are same number of H plus and HO minus. That means in place of HO minus, you can write as if H plus. So it means what? It is basically H plus square, and that is equal to 55 into 10 to the power minus 40. Next you have to take root, that is to the power half. Sorry, it is minus. So we have already reached our answer because we got H plus. Next thing, very simple, pH you have to find, which is negative logarithm of H plus, and H plus concentration we have here 55 multiplied by 10 to the power minus 14 to the power half. So half will be before log. So here I can write, as it is 55 multiplied by 10 to the minus 14. So it will be log 55 plus log 10 to the power minus 14. Now log 55 is given. So you can write it 1.74. And log 10 to the minus 14 will come before log, and log 10 is 1. So basically it is minus 14 only. Minus 14 multiplied by log 10, and log 10 is 1. So you have to write it like this. Now minus half, and this whatever you have within third bracket, that is also negative. So negative negative will be cancelled, and it is 12.26. 12.26 means, even if you do not do the full calculation, 12.26 means it is something 6 point something, because 12 by 2 is 6. So 12.26, 6 point something. So that is enough to choose the correct option, which is the last option, option D. Okay. Now, without doing calculation also, you can easily neglect these two options, because when it is 25 degrees centigrade, then only the pH of neutral solution is 7, right? And as with increase in temperature, Kw value increases. So H plus concentration, that is, sorry, pH I am talking about, pH will always decrease. So these two values cannot be correct answer. 7.87 cannot be correct answer because it is greater than 7. So whenever you have Kw value greater than 25, it may be 50, 60 degrees centigrade, 70 degree, 100 degree, it will always be lesser than 7. Now whether it is 5.13 or 6.13, that we have to calculate. But B and A cannot be correct. So this is correct. Here, how with increase in H plus, how the pH is changing, that information you can get. So as it is logarithmic scale, right? pH scale is logarithmic scale. So when you are changing concentration of H plus by a factor of 10, suppose first the concentration is 10 to the power 0, that means it is simply 1. Okay. Then we have 10 to the power minus 1, which means it is 1 by 10. So from 10 to the power 0, that is 1, you are moving to 10 to the power minus 1. So you are moving from 1 to 0.1, which is 10 times increase. So when you are increasing the H plus concentration 10 times, look at the pH value. For the first one, 10 to the power 0, the pH is basically 0 because it is log 1, negative log 1. Now for the second one, negative log of 10 to the power minus 1, which is 1. So when we are moving 10 times decrease, you can also consider the second one, from 10 to the power minus 1 to 10 to the power minus 2. This is also 10 times. So all these are basically 10 times. And when we are changing the concentration of H plus 10 times, the value of pH each time is changing by 1 unit. Okay. And it is possible because it is logarithm. Now, one important information that we have to keep in mind, that is important when you will solve any problem. Though it is true that we use the formula for calculation of pH, what we use negative logarithm of H plus concentration. But you have to keep in mind, when you will directly apply this formula for calculation of pH, and when you are not, you cannot use this formula directly. So you have to remember this condition that I am going to discuss. So when concentration of H3O plus or H plus, it is greater than 10 to the power minus 6. Greater than 10 to the power minus 6 means, suppose it is 10 to the power minus 2, 10 to the power minus 3, 10 to the power minus 4, like this, greater. In this case, you can use this formula directly. There is no such problem. That means when it is 10 to the power minus 2, you can say that it is 10 to the power minus 2, you can say it is pH2, like this. Okay. But as concentration of H2O plus, it is dilute. That means lesser than 10 to the power minus 6, 10 to the power minus 10, 10 to the power minus 11. So in this case, what will happen? Directly using this formula, it will not give you correct result. Okay. Now why I am saying so? So suppose, and why it is so? It is because contribution of H plus from water also you have to consider. So when it is concentration 10 to greater than 10 to the power minus 6, under this condition, contribution of H2O plus that you are getting from water, it is not so high. Basically, concentration of H2O plus we are talking about, that means it is an acidic solution. Okay. Now, acidic solution means it is present in water. So acid plus water is also present, and from water also there is a chance of getting H plus. So it is not that you are getting H plus only from the acid. You can take acid, suppose HCl. You are also getting H plus from H2. But in this case, you can neglect it because the acid is more or less concentrated around 10 to the power minus 6 or greater than that. So under this condition, contribution of H plus from water you can ignore because it is not very dilute solution. But when it is lesser than 10 to the power minus 6, then contribution of H2O plus that you are getting from water, that you cannot neglect. So lesser than 10 to the power minus 6 means it may be 10 to the power minus 8, 10 to the power minus 9. So these are basically very dilute solution. So when it is very dilute solution, suppose 10 to the power minus 8 molar HCl. Now very dilute means what? The contribution of H plus that you are getting from water molecule, now you cannot ignore it because it is very, very dilute solution. Okay. Now if you are now using this formula, you will not get correct result. So suppose I am saying find the pH of 10 to the power minus 8. Now if you are putting this in this formula of pH, what pH you will get? You will get pH that it is 8. But it is 10 to the power minus 8 molar HCl. And how the pH of HCl solution? It is true, it is very dilute. But how the solution of HCl? How you can get pH 8? pH 8 means it is towards basic side. But for HCl solution, even if it is dilute, it is not possible. So logically, it is not right. You are not getting correct result. So now you also have to consider the contribution of H plus that you are getting from water. And that we are going to do next. One more point, pH of a solution we can find roughly with the help of pH paper. So there is a specific paper found if you it comes in contact with the solution for which you want to know the pH. There is some specific values and the corresponding color mentioned. So from the color you can understand what is the pH. And another instrument is also there, which is pH meter, and that is it will give you very accurate value. So these are some ways by which you can find roughly the pH of a solution. Okay. Next, we will solve a problem where you will be able to see that how, not by directly using the formula minus log H plus, when concentration is lesser than 10 to the power minus 6, like this example, 10 to the power minus 8 molar HCl. For this solution, what is the pH? So if you are directly using the formula, you will get pH value 8, but that is not correct. The pH value should be lesser than 7. It is very dilute, but pH cannot be greater than 7. It has to be lesser than 7. So how to solve this type of problem when it is lesser than 10 to the power minus 6? So it is not something very difficult. See what we are doing, as it is HCl. So there is H plus you are getting from the dissociation of HCl. And from H2 also you are getting some H plus. See, there is equilibrium sign. And the equilibrium, it is mostly remain towards the left hand side because dissociation is not so high. Water is it is weak. Dissociation is weak. But for HCl there is a single, that is only one side arrow. That means it is mostly in the dissociated side. H plus Cl minus. So H plus we are getting, that is the total H plus concentration, that is basically contribution from water as well as contribution from HCl. Now contribution from water, you can write 10 to the power minus 7 because we know from Kw that H plus and HO minus, that is basically equal to 10 to the power minus 14. And if you consider neutral, that is a water, but if you consider neutral, this is also equal to H plus. So H plus whole square equal to 10 to the power minus 14. So H plus is 10 to the power minus 7. So in place of H plus, which is coming from water, you can write 10 to the power minus 7. But from H plus, you have to write this value, which is already given in the question. If you take common 10 to the minus 7, what you will get? You will basically get, if you are taking it common, you will get 1 plus 0.1, which is 1.1 into 10 to the minus. Now you can use this formula of pH, put H plus, which is 1.1 10 minus 7. So there is a negative sign. So log 1, 1, this is negative, and 7 minus something. So it is giving you 6.958. See, this is lesser than 7. So directly don't use this formula. You have to solve it in such a way. Now, though we are doing it in this way, but if you follow the ideal way of solving the problem, that also I will show. Though both are giving you almost same result, so for saving time, in this way if you solve it, it is okay. But still I want to show you that is the ideal way to solve this type of problem. So Kw is, we know it is multi H plus concentration, that is ionic product, multiplied by HO minus. Now, in this case, we have approximated the contribution of H plus, which is coming from water. We have approximated it as if it is 10 to the minus 7. But ideally, if you want to do so, because it is not simply water, there is also, it is mixture of HCl and water. So directly putting the value of 10 to the power minus 7 in place of H plus, which is coming from water, that is not ideally correct. So what we are doing here, as if the contribution from that is H plus, which is coming from water, suppose that is X. Now ionic product, it is always same as long as you are not changing the temperature. So Kw value, it is always 10 to the minus 14. But in the right hand side, in place of H plus, now you have to write X plus 10 to the minus 8, because when it is H plus, X is coming from water and this is coming from HCl, and this X for HO minus, because it is also X. If H plus from water is X, HO minus is also X. So in this way we are getting this type of equation, X square 10 to the power minus 8X and 10 to the power minus 14. So this is equal to 0. Now this type of equation, it is basically, in general, if I write, it is AX square. Here A value is 1. Then we have BX. So B value is 10 to the power minus 8. And C in our case is 10 to the power minus 14. So comparing this with this equation we are getting, and to solve this type of equation, the value of X, that is equal to minus B plus minus root over B square minus 4AC divided by 2A. So there will be two values, but we will take only the plus, that is a positive one. So here if you compare A, B, C, these three, so if you want to get the value of X, which is that is H plus concentration that we want to know, in place of B, A, C, you have to put these three values. So when we are doing it, so here we have written minus B, because B is 10 to the power minus 8. Then we have written B square, 10 to the power minus 8 square means 10 to the power minus 16. Then 4, then A is 1 and C is 10 to the power minus 14. Negative will be cancelled, so ultimately it is positive. Divided by 2 into 1, that means it is 1. Now we will take only the positive sign, so that is why here it is written plus. 10 to the power minus 7, you can bring it out of root because it is common, and inside there will be 1 divided by 100, which is nothing but 10 to the power minus 2. Okay, so 10 to the power minus 2 plus 4. Basically here 10 to the power minus 14 you have to take common, but as it is out of root, ultimately it will be 10 to the power minus 7. And inside it is 4 plus 10 to the power minus 2. So once you are finished with the calculation of X, this is the value of X. Fine. So H plus concentration, now we can write as it is X plus 10 to the power minus 8. So in that place, if we put this, and then finally if you do the calculation, then also pH value, see, just compare. So even without doing this lengthy calculation, you can get that is by applying this approximation, that is by putting in place of H plus coming from water. If you simply do this approximation as if it is also 10 to minus 7, so we are getting almost same answer. So if there are some options, you have to choose this value, okay, which is slightly lesser than 7. What is the pH of the resulting solution when equal volume of 0.1 molar NaOH, 0.01 molar HCl. So here concentration is 0.1, here it is 0.0. So we have taken strong base and strong acid. Some options are given. Now strong acid and strong base we have taken, but they are not equal concentration. So don't think they will be neutral. Normally what we know, strong acid, strong base, strong acid is neutral, provided they are same concentration, but it is not same concentration. So there will be some limiting reagent. NaOH HCl, when they react with each other, it is 1:1 reaction. But here concentration of base is high. So initially, and see, it is equal volume. Now this is basically concentration. But as it is mentioned equal volume, so suppose it is V ml, this is also V. Now if this V we consider as if it is 1 liter for both, then what will happen? As it is 1 liter, so this it means 0.1 molar means 0.1 number of moles of NaOH present. So considering is as if it is 1 liter, initial number of moles for NaOH is 0.1, initial number of moles for the acid is 0.01. So here all HCl will be consumed. So 0.01 moles of HCl, it will react with 0.01 NaOH only. That means remaining amount 0.1 minus remaining amount, there will be unreacted NaOH. So final value of NaOH 0.09. So it is 0.09 and this is 0. All are consumed. Now come to the right hand side. NaCl, this is also, it will be produce similar number of moles. So if 0.01 HCl reacting with 0.01 NaOH, obviously NaCl is also 0.01, water is also 0.0. But we are interested only in the pH of the solution. That means we are interested in this part. So here HO minus concentration is basically you are getting from this value. So HO minus concentration is 0.01 number of moles, but that is present in 1 liter. So you have to divide it by 2. Even if it is not 1 liter, as you have mixed V volume to another V, that means it is double dilution. So that is why concentration should be now half. So when dilution is double, concentration is basically half. So this is the final concentration of hydroxide iron. As you know the hydroxide iron, first simply calculate pOH, which is negative logarithm of HO minus. So log 0.045, this is the value, but we need pH. Don't think this is the value of pH. It is pOH, right? Because excess HO minus is. But we know that pH and pOH, basically what is the relationship between these two, that we are going to discuss next. This is actually equal to 14. So that is why if you use this formula, that is 14 minus pOH, that will give you the value of pH. And the last option is the correct option. So now we are going to see this relation that we have just used, relation between pH and pOH. This is actually equal to 14, but how we are getting it? We know that Kw is equal to this ionic product, and at 25 degrees centigrade or 298 Kelvin, this is the value of this equilibrium constant. Now if we take negative logarithm both sides, it will be minus log Kw. So it is pKw, just like minus log H plus is pH. So minus log Kw that is pKW. And in the right hand side, when you take log 10, you will get simply 14. Now Kw, that is also equal to multiplication of these two factors. That means instead of writing Kw, if you are writing these two, and then you are taking negative logarithm both sides. So negative log of H2O plus, because it is multiplication sign, plus negative logarithm of HO minus. So see what we are doing. First, simply take log. There is a plus sign because it is multiplication. Log 10 H plus, log 10 HO minus. This side it is simply 14. Now minus 1, if you multiply both sides, you can convert this term to pH, because this is pH and this is pOH. So this equation, if you write pH and pOH in the left hand side, and in the right hand side if you write pKW, you will get this relationship. So this is the relationship between pH and pOH, which we have just used in the previous problem. Okay. We already know that with increase in temperature from 0 to 10, value of Kw increases, which is clear from this. See, at 30 degree it is 1.5 10 to the minus 14. But when you are moving to 40, 50, power is same, but still there is slight increase. It is very slow increase, but still there is increase. Now, if you look at the third column, here we have the H plus. So when you take root of Kw, why we are taking root of Kw? Because H plus square is Kw. So H plus, if you want to get, you have to take root of Kw. So by taking root of Kw for each of these, you are getting the H plus concentration. And when you know the H plus, you can also find the pH by using negative log of H plus. Now look at the value of pH. As if with increase in temperature, as you are moving down, there is increase in temperature, and as if with increase in temperature, pH is decreasing. Remember one problem we have solved today, where at 100 degrees centigrade, pH is something 6.13, right? So pH is decreasing, though this is slow decrease, but it is decreasing. Now don't make the comment that with increase in temperature, the water is becoming acidic because now it is lesser than 7. No, this is not a correct comment. This comment we cannot make. Neutral pH 7, this is true only when it is 25 degrees centigrade. But when you are changing the temperature, the value of Kw itself is changed. So the scale of pH, now you cannot say that neutral is pH 7. It is true only when 25 degrees centigrade temperature is maintained. But when you are increasing temperature, Kw value itself is changed. So similarly, the neutrality point, it is no longer 7. Similarly, you can say that, you can see here, when you are moving, keeping 25 in the middle, when you are increasing, the values are decreasing. Similarly, if you decrease the temperature, value of Kw is also decreased. Now pH values, that is the pH for neutral point or pure water, that is also greater than 7. But that doesn't mean that it is basic. So don't think in that way. So although Kw may change with temperature, and there is variation in pH also, but this is very small, so sometimes we ignore it. pKw is very important quantity for aqueous solution, and it controls the relative concentration of H plus and hydroxide ion, because their product, that is H plus multiplied by HO minus, this product is always constant as long as you are maintaining the temperature. It is dependent only on temperature. So that is why this equation, that is Kw is equal to H2O plus HO minus, it is very important, and it has several applications also. For pure water, that means it is neutral. pH increases, pOH decreases with rise in temperature. So here pH is increased, this is decrease. Then the second statement, decrease, increase, that is the reverse. Third statement, both are increased. when you are increasing temperature, because statements all are with rise in temperature. This is common. And in the last option, both are decrease. Now, which one is true? So, what you have seen in the previous slide, that pH is decreasing with temperature. But what about pOH? Actually, pH and pOH, these two, there will be similar effect, right? Now, first consider this graph. If you draw this by taking pH in y-axis, temperature in x, we know pH value, it is when it is around 25 degree, the corresponding line, it is 7. But if it is 40, now it is less. If it is 10, it is higher than 7. So pH is decreased, that is fine. But what about pOH? So these two are basically always the same when it is neutral or pure water, because both are temperature dependent. So when you are considering, that is Kw, it is H plus and HO minus. So when Kw value itself is changing with temperature, suppose with increase it is increasing, decrease decreasing, equal effect will be there for H plus and HO minus. You can also use the other relationship, that is 14 is equal to pOH and pOH, and these two are always same, right? As if it is 2 pH or 2 pOH. So there is similar effect because it is pure water or neutral. So total number of H plus, that is always equal to total number of H. So that is why, as long as it is neutral, whatever is the temperature, the effect on pH, it will be same. So if you are decreasing temperature, both will increase. If you are increasing temperature, both will decrease. So correct option should be the last option, right? Assertion reason type of problem, we have to find correct option. Assertion, the statement is saying pH of water increases with increase in temperature. Now that is not correct. It is false, because we have seen there is decrease. What about the other statement? It is saying the dissociation of water into H plus ion and HO minus ion, it is exothermic. So it is talking about this. So any dissociation, it cannot be exothermic. It is basically endothermic. So this is also false. So this table will help you to understand that how pH is decreasing as we are increasing temperature. So first statement cannot be correct. And dissociation of H2, it is endothermic, not exo. So both are false. So both assertion and reason statements are false. Ionization of weak acids and weak bases. We know that we use for weak acids Ka, which is dissociation constant. For weak bases we use Kb, and that we have already seen. For strong acid we do not use such terms. We do not deal with Ka or Kb because there is complete dissociation. So the value of Ka, Kb for strong acid and bases, it is very high, almost close to infinity. So that is why we don't talk about Ka or Kb for strong acid and bases. It is only for weak acids and weak bases. Here we have taken a weak acid in general. Suppose the formula is Ha. It may be H2SO4 HCl HNO3. Sorry, weak acid. So it is considered as if it is acetic acid. Ha. A is CH3COO minus and H. It is partially ionized because it is weak. And how we can express the equilibrium of Ha? So you have taken Ha in water. This is solvent. This is physical state mentioned aqueous. After that is dissociation, in the right hand side we have hydronium ion aqueous and A minus. That is a conjugate base. So initial concentration in terms of moles. Suppose C moles of Ha is present in a particular volume, and at first these two you have to consider 0. Now at equilibrium, suppose only alpha fraction of C is dissociated. So first you can write it as if it is C minus C alpha. So dissociated amount is C alpha. So the remaining concentration of Ha should be initial concentration minus the fraction that is dissociated. Now the fraction that is dissociated is C alpha. So just subtract it from the initial moles, which is C. So that is it is C minus C alpha, or you take C common, it will be C into 1 minus alpha. So C into 1 minus alpha, we are not writing any value for H2 because it is before and after dissociation, the concentration is same. So it is meaningless you put any, you consider it, you don't need to. And what about right hand side? As it is 1:1, that means when 1 mole of HA is dissociated, 1 mole H2O plus produced, 1 mole A minus. So when C alpha amount is dissociated, here also it is C alpha H2O plus, number of moles of H2O plus, number of moles of conjugate base A minus, that is also C alpha. So this alpha is known as degree of dissociation. So degree of dissociation we use for any weak electrolyte. The fraction of total number of moles of an electrolyte that ionizes or dissociates into ions in aqueous solution at equilibrium is called as alpha degree of dissociation. Mostly it is denoted by alpha. That is the common convention followed. So this is a fraction of total number of moles. Fine. Alpha is generally very low value, fraction 1. So now we know the equilibrium number of moles for HA, for H2O plus, for A minus. What we'll do next? Ka. So Ka is equal to concentration of whatever species you have in the right hand side and divided by concentration of HA. Concentration of H2O not required, it is present in excess. Now in place of H2O plus you put C alpha. Basically you do not need this third bracket anymore, simply this bracket will do. And C square alpha square, C common, CC will be cancelled. So ultimately you are left with this type of expression, C alpha square divided by 1 minus alpha, right? Now here, though we already know the fact, but here still you can understand this relationship, that is larger the value of K for weak acid, stronger is the acid. Now from this expression you can understand this. When Ka value is high, that means this numerator part, H2O plus A minus, these two are very high. So obviously, if numerator part is increased, Ka will also increase because it will mostly remain in the dissociated form, and undissociated form is not very high. That means mostly it is dissociated. So it is stronger acid. Suppose you are comparing two weak acid. You know the value of two weak acid, one is X, another one is Y. So for this, suppose there is a particular value Ka for X, for Y it is Ka of Y. Now if you know these individual values of dissociation constant for X and Y, these two weak acid, now you can compare, though both of them are weak, but which one is more weak. So among these two, relatively which one is stronger, that you can decide from the value of Ka for X and Y. Larger the value of Ka, because now the numerator, these two values are high, HA is low, but if it is Ka value is very low, that means HA is significantly present, not H2O plus or A minus. Similarly, just like weak acids, you can also consider weak bases. So weak bases react with water to produce hydroxide ion as shown in the following general equation. So in this case, we will consider as if capital B is the general representation for any parent base and its conjugate acid is protonated form, which is BH plus. So in the previous case, A minus is the conjugate base of HA. Now BH plus is the conjugate acid of B. Conjugate acid base pair means there is a difference of H, right? So B aqueous, H2 aqueous, this is better to write L. So initial number of moles C, this is 0, this is 0, this is. Now suppose C alpha is the fraction which is dissociated. So when C alpha is dissociated, obviously these two produced is also C alpha. Now at equilibrium the remaining amount is C common 1 minus alpha, and these two as usual same. So same type of expression you will also get in this case, which is ionization of weak bases. But now we will use Kb, not Ka. So Kb is concentration of BH plus conjugate acid, concentration of hydroxide ion divided by undissociated BH2O liquid neglected, right? So here we will put the same thing. So what we are getting? C alpha square 1 minus alpha. Now same conclusion also here you can draw, which is larger the value of Kb, stronger is the base. The same, because when it is larger Kb means dissociation is high. Suppose you are comparing two bases, dissociation high means these two species in the right hand side it will be high. That means numerator value will increase, denominator is less, and also the reverse statement, smaller the value of Kb, weaker is the base. So from Kb values of different bases you can compare, you can arrange their strength. Okay. So see, in this table you will get information of different weak acids. So the first, here you will get all the weak acids, weak bases, diethylamine, ethylamine, ammonia, hydroxylamine is NH2OH, pyridine is organic base, just like benzene ring, but one carbon is nitrogen. Aniline is NH2 attached to benzene ring. Fine. C6H5NH2. So all are reacting with water. In this case, hydronium ion we have written, and here HO minus. Fine. So look at the K values. 1.6 and 12. Just look at the this one and this one. Here 10 to the minus 12. This is minus 1, which is for iodic acid. This is for hydrogen peroxide. So here the value is very low. That means hydrogen peroxide compared to iodic acid, it is weaker. According to the relationship, larger the value of K, stronger is the acidity. Now you can also write compare the pK. Now pK and K, these two are inversely related because Ka is negative log of, pKa is negative log of Ka. So when K is very high, so when Ka is increasing, that means pKa is decreasing. These two are related to each other inversely. So see here pK is 0.8 and here pK is so high. So when pK value is very high, that means the corresponding acid is weak. So just I'm considering these two extreme. In this case Ka max, here Ka minimum, but in this case pKa max, but here pKa minimum. Same thing you can also see for the basic strength is increasing as you are moving up. Here Kb value 10 to the minus 4, for aniline 10 to the minus 14, very weak compared to diethylamine. pKb value for aniline is high, here it is 3.16. So in this way you can understand the relationship, that is when it is strong acid or base Kb high, but pKb less. Okay. So we'll end here, completely new topic, will not start today. So that's all for today's class. Thank you for listening.